Um, this is definitely an experiment. Haven't done this before in this format, obviously. We've definitely had a lot of opportunity to um, work with 40 Flow over the last couple of years, and you know, built it into our practice. But one of the challenges has been sharing that with other people, because everyone's kind of got a different perspective to you know, how they want to run their cardiac imaging services, and what role of technology there is in that, and sometimes it takes a little bit of time for people to adopt new things into their practices. So to help people figure out, you might want to mute, figure out whether 40 Flow is something that they want to build into their practice. The only way to really get at that is to get some hands-on experience one way or another, to see if it's worth the investment of going through and learning that new technology. Hey, Brad, I see you joined as well. I'm going to just sort of help you guys get that perspective just by walking through some of the cases in our from our practice here at UCSD. So I'll just go ahead and share my screen and get started. Okay. Do you guys have any hopes or wishes for what you would like to see before I get started, so I can emphasize it, or feel free to unmic or unmute your mics. Brad or
I know. Hey, hey Albert, thanks again for including us in this, and Lisa, thanks for organizing. I know from our perspective, we are just really trying to ramp up clinically what we do with 40 Flow, and we particularly have been using Circle. So I think, one, seeing how you guys are incorporating it on a more daily basis, and then also just more familiarization with Arterys would be excellent from our standpoint.
Okay, that sounds good.
And this is Lisa. I'll be starting at UT Southwestern in a little under 2 months. And I one of my first tasks as an assistant professor is going to be hopefully establishing a 40 Flow program. And that would also involve a software licensing agreement to get that set up in the first place. And I'll be mostly working with adults, possibly with the expansion of cardiac MR to the PEDS hospital in Dallas. That's kind of a very not definite thing. But yeah, I just would love to see the inner workings of Arterys. And for instance, we just did a 40 Flow cardiac MR on a 5-year-old who had a superior sinus venosus ASD. And that itself was actually not super easy to visualize on the 40 Flow. And it wasn't, it was at least a medium-sized one. It certainly wasn't a very small ASD. And so I don't know if you have any cases in PEDS, but specifically how easy it is to visualize smaller flow that is abnormal. To me, something like that would be useful, that high resolution.
Okay, that sounds good. And I think that's one reason to have this meeting, is just to also kind of highlight and sort of break misconceptions and sort of show what's possible in a way. I think people are coming to 40 Flow with a certain idea in mind of what they've done and been able to experience with it, and the struggles that they've had with either the pulse sequence, an earlier version of it, or the software that they're using. Maybe it's maybe not the easiest to use to do what they're trying to do. This software that Arterys is providing is really based on a software that I originally wrote when I was a resident it's almost like 10 years ago now. It is 10 years ago now. And the purpose of that was really to change the way that we look at 40 Flow and make it actually clinically usable. And so, I don't know, are you able to see my screen here?
Yes.
Okay. The the idea is that this pulse sequence is very complicated in the way that it generates images. What one of my mentors, Arterys, was doing at the time was building in parallel imaging compressed sensing into pediatric imaging in general, and developed a really amazing pulse sequence for 4D flow specifically, but also for multi-phase contrast enhanced MRA and a bunch of other things using the combination of those two technologies. And that was like 10 years ago, right? So what I noticed at that time was that the 4D flow data was very high dimensional, and it was very hard to deal with. There was no software to visualize anything. It wasn't written. The software that we were using was like Insight and all these engineering applications. They weren't really designed for physicians to use. So I ended up writing something completely new because I felt like there was a lot of room for improvement. And eventually that prototype we used all the time for all of our 4D flow cases. The 4D flow was at that time done as an addition at the end of the cardiac MRI. So it was like a 10-minute acquisition at the end. But since then, about 2-3 years after that point, we started moving the 4D flow pulse sequence to the beginning. And when I started as faculty at UCSD, that's basically the protocol that I established, is that for all congenital heart patients, we do 4D flow at the beginning. And I could show you a more complete case later on. I'll just show the 4D flow stuff for now. But basically, we run 4D flow for every congenital heart, every structural heart case that we care about. There are a couple basic elements to 4D flow that every software should have, that not every software does have. And one is a good background correction. In the early days of phase contrast, and up until we started implementing this in my software, was an algorithm for correcting the background phase error. And that coming from an engineering background, the very first thing that I noticed when I was measuring flow as I was going up the ascending aorta was that it increased when I measured at different segments of the ascending aorta. So I realized this was a problem, and I kind of asked around to the different faculty when I was a resident what the solution was to this, because I didn't understand what was happening. And they said, oh, there's eddy currents, there's things in the magnet that are causing the data to be not accurate. And I was like, oh, okay, well, then what do I do? I think, I can fit that data. I can fit the background soft tissue. I found an old paper from like 2001 of a group doing it in 2D, and I implemented the algorithm in 3D. And then that was actually the very first patent that I ever wrote for Stanford. And then Arterys implemented something even better, an algorithm that can run instantaneously. And so this is a real-time implementation of that background phase error correction. So what you see here is the use of that phase error correction. And what we're trying to do, and this is all done in the background, I'm just showing it to you, but in the background of the software is an automated, even deep learning implementation of that phase error correction. Okay, so this is just an example case. We run 4D flow for every patient that we send over here to a magnet that has the 4D flow pulse sequence running. You'll see a couple different things right off the bat. I make a couple of adjustments. Let me just sort of reset the view so that you can see what we start with. You have on the 3 panels, axial, coronal, and sagittal. This acquisition is for the full chest. It's just an axial prescribed volume from top to bottom. You can see the full extent of the coverage. This pulse sequence ran, let me see here. or on a 3T magnet that we have downstairs in ACTRI, with a resolution of about 2 by 2 by 3 millimeters, and I use a flip angle of 25, and a scan time of roughly about 10 to 12 minutes. This is a very highly accelerated using compressed sensing, but it's not like ridiculous, you know, it's like 1.8 by 2, two-dimensional acceleration. So a total acceleration factor of 3.6. And this gives us a chance to scan this in a meaningful way. I don't want to scan it in 2 minutes because then the data looks really noisy. And I want to scan it for 30 minutes because that takes too long and patients may move during that time. But
can I interrupt with a quick question? I see the VANCs listed. Are those in the 3 like X, Y, and Z dimensions? They're the max only, or?
Yeah, that's a great question too. So we typically scan at 150 centimeters a second for patients with indication of PAPVR or ASD or Fontan circulation, where I'm not expecting very high velocity flows. And the reason for that is because I want to optimize this for venous flows, right? Venous visualization of small vessels like the PAPVR or a sinus venosus defect or small ASDs or Fontan flow. Those patients, you really want to optimize your VNR. In patients who are expected to have high velocity flows, like tetralogy of Fallot with a pulmonary valve stenosis, coarctation, VSD, I will typically use a bank of 350 bicuspid aortic valve. So I will use the patient history to prescribe the bank. That is the only sort of variable that we have to adjust on a per patient basis. But that can be done without looking at an echo or anything if you want. You just need to know the clinical history and indications. So typically 150 for low velocities, ASD, PAPVR, and 350 for coarctation and that kind of stuff. Some patients you may find, you know, have Fontan plus a coarc. But the priority in the Fontan patients is to quantify the veno-venous shunts, and they typically have relatively low flows from their single ventricle. So I don't really care too much about the coarctation. Nobody really complains about that, that you weren't able to get the peak velocity in a coarc there. And if you absolutely had to, you could still do a one cut of the coarc or whatever with a 2D cut if you absolutely needed it. Or you could do a dual bank, which is also an option too. So anyway, that's how I choose: low bank 150, high bank 350, and anything that I'm not sure about, I'll put intermediate 250. So that's kind of meaning if for general use, general indication, for congenital heart disease, I'll use 250 as intermediate when I'm not sure what the main indication is, or I don't have any history or any prior information. So that's a little bit about the background of the how we acquire. We put together a paper, hopefully that'll come out one day, on exactly the technique and what we use this for. As you can see, this is a patient with PAPVR. And there are a couple settings that I make adjustments for typically. When you first open up Arterys, the standard settings are going to be like 90, 88, 85, something like that. And the arrows are off. This is okay. One thing that I implemented in my version of software is when you hit V, the vectors, turn them on, I automatically toggle the anatomy and speed filter down so that the arrows stay on the vessels. And then when my version of the software, I hit V again to toggle them off, this slider goes back up. But you can manually do that yourself too. So that's basically what I do. Maybe one day we can implement that in Arterys as well. But it provides some very basic visualization, right? Like you can see the right lower lobe PAPVR pretty immediately. And it doesn't take much adjustment. this is very clinically practicable, right? You don't have to like do pre-segmentation of a vessel or any funky stuff. It just is already good. But you know, people may have their own style for how they want to interface with 4D flow. Does that answer your question, Lisa?
Yes, it does.
I'll just walk you through this case. You know, in this case, what I will typically do for PAPVR and ASD, I'll rotate into a short axis and sweep through. Oh, look at that! It could be a small little ASD. I'll sweep through in short axis. I haven't actually looked at this case, so let me just take a look. Now, oh, it's just a yeah. It's not, so you can rotate and you can see that it's not an ASD. It's actually just volume averaging in that slice. You can control the thickness of the slice by using this tool up here. And that's just a pulmonary vein that's coming in behind the atrial septum. But you can sweep both in short axis and long axis to try to figure out whether there's a atrial septal defect. In effect, what you try to do on the scanner is basically the same thing. You will sweep, you'll create an axial stack often, or a short axis stack, extending your short axis from the LV all the way back to the back of the septum to try to prove to yourself whether or not there's an ASD. In this case, you can see that it was just a pulmonary vein that was fooling me, and there was not actually an ASD. But that's how an ASD will look. Just not in that location. An ASD, like a secundum, would show up here. I can show some cases of that later. Now, for blood flow measurement, which is one of the main principal reasons to use 4D flow, it's actually quite easy. We can do either direct or indirect flow measurements. So let me just sort of walk you through that. There are a couple different tools that make that a little bit easier. One is this flow direction tool. It just looks at the velocity at that position and creates a cross section at that location. And this is one of the, I built in a lot of really neat little cute tools to make my life easier, because as a resident, I didn't have a lot of time to process a lot of cases. So I spent my time developing quick tools to be able to gather data quickly. And this was one of them, is just taking the flow direction and then cutting it. And using that as the normal vector of the plane. Very simple. And it gives you basically a good plane. You can adjust it, you can rotate it, or you can either control these little things like most 3D post-processing software. You can reorient it however you want. So this is perpendicular roughly to the lumen of the vessel. You can hit 7 to get you a phase kind of a more conventional looking view from phase contrast. This just takes the dot product of the normal plane, the vector of the plane to with the velocity vector field. That's pretty much it. I don't know. So this is the right lower lobe pulmonary vein, but you can, that anomalous pulmonary venous return. Okay, so it looks like I measured this before, 3.8 liters per minute, and when I did it today, I got 3.7 liters per minute. That's not unusual to get very similar measurements, and you can actually see where I did it last time. The two measurements are pretty close to where I measured last time. I can measure somewhere else just to get a feel for it. But by being able to do repeated measurements, you can quickly see whether or not your data is too noisy. That actually is a problem. When you do 2D phase contrast, you'll find that when you do 3 or 4 measurements, they can be rather different. And that's more about the intrinsic noise of your acquisition. That's like my engineer speaking, is that if you really want to know the truth, you have to do multiple measurements. And then hopefully the measurements are similar. If they're not, it tells you that your instrument is not very good. So anyway, that's yet another reason why I do a low vein, because I have gradually learned that for Fontans and for anomalous pulmonary veins, there is some noise, right? So here's 3.7, 4.1, and 3.8. So you can get kind of a really anchored down thing about what the actual flow is through that anomalous vein. Okay. Then you can look also, I've done this already for the aortic valve, you know, like a nice smooth waveform, not very noisy. It tells me my acquisition is pretty good. And you can even see this rebound reflective wave come in. And so it's got a really nice waveform. Here's another waveform that I did at the aorta, ascending aorta. And the measurements were like 4.2, 4.8, you know, repeated measurements 4.9. I often find that measurements directly at the valve where I was taught to measure tend to be a little bit lower for reasons that I don't fully understand, but I suspect it's just because there's a lot more motion artifact that is getting averaged out. I often find that the ascending aorta is more reliable. The exception to that is in patients with bicuspid aortic valve. They will have very unreliable ascending aortic measurements, as we showed in a recent paper in Radiology cardiothoracic imaging. We think may be related to flow vorticity. So that is the exception to that. But in general, we measure in the ascending aorta. And then I've done similar measurements you can see previously of the pulmonary valve, which I've sort of recalled by clicking on it here. So 8 liters a minute. Now, that's kind of the way I think about this. 4 liters a minute, 8 liters a minute, 4 liters a minute. You know, so the things add up, right? The anomalous pulmonary venous return contributes 4 liters of flow, roughly. The pulmonary valve is showing us 8 liters a minute are coming out of the right heart into the pulmonary arteries. And what's actually coming out, what's coming out of the ascending aorta and near the aortic valve is roughly 4 and 4.5 liters a minute. That's the amount of precision that I think we really need, and the amount of precision that the technology offers. It's not like within 0.01 most of the time, but sometimes it is on accident. But really within half a liter, within quarter liter a minute is the resolution of flow. Does that make sense? Hopefully this is a pretty straightforward example.
It does to me.
Yeah, it does. Hey, Albert, do you guys do 2D phase contrast still as a part of these studies, or are you doing all of your flow and velocity off of 4D?
So no, we don't do any 2D phase contrast anymore. When I first started, the very first year or two, I did do that because I thought 4D flow wasn't accepted at the time, and I was worried that I couldn't get things published if I didn't include 2D. And that was 6 years ago. I stopped that because it was pretty much useless. I never relied on the 2D, and they were often really off. And I knew that was the case, but I was really just doing it as a fail-safe for publication. Then I started publishing and just citing my old papers. That's been long established, and I found that no one really complained about that. I mean, some people wanted me to take the few cases that I still did of 2D and put it in an appendix, but I was literally doing it only for research purposes. And so I stopped that. And then that also prevented, simplified our protocol. Now this protocol runs and I'm never there, right? Like no faculty ever goes to the scanner for a congenital heart case. And that's the big value add. That's the reason why we pursued this, why the company, why Arterys took this on as its primary product when we first started, is that was the value proposition, is that by using 4D flow, you no longer needed to go to the scanner and the techs could just run the simple acquisition on their own. And so I decided to shift the protocol and no longer run 2D. But from time to time, we may throw it in just for fun. It's a coarc, and I might use it, to teach you know, to get a peak velocity, this is where you have to measure. But most people learn that from the 40 flow anyway. So I don't really do that. I just, you know, we may just sort of keep the knowledge alive by doing a few here and there, but I generally do not include it as part of the protocol. Hope that helps. A couple facets of this. Now, there's going to be reasons why you might want it. Is that, say you run a bank of 150 and you don't have a dual bank acquisition available to you. You may say, well, in this case, I care about a coarc. Let me see if I can find a different case. It doesn't come up often, and for me, I just don't do it. But let's move off of this case so that we can look at something else while we still have time. Does that answer your question at least?
Yeah, absolutely. I think what we run into sometimes is that I would like to go that route, but people are still, you know, some faculty are still less comfortable with the idea that 40 flow is adequate for this purpose. And
it may depend on what scanner and what equipment and what pulse sequence you have. It's possible that you're not getting images like we are. The quality. This is one of the noisier cases in my tool chest. This is a bank of 350, and you can see that in this setting, you know, you might not. This case, I would not rely on for small ASDs and anomalous veins. The patient comes in with a history of Shone's or left-sided disease. So I start off with a bank of 350. In a case like this, if I get flow discrepancies between, you know, a QPQS of 1.2, I'm not sure that I'm not missing a small ASD. But I'm not too worried about it because that's the least of the patient's problems. That a small ASD is always possible, but I will generally see it. I just might not be able to measure it reliably. But you can see it's a little bit noisier, right? The velocity to noise ratio is, you know, it scales, or it scales with the bank. It's a fraction of the bank, right? So like maybe 10% is the noise level, noise floor. And you can see that, you know, the arrows are going in slightly different directions because the noisier acquisition. So I can see that if you acquired all of your 40 flow at a bank of 350, and then you're looking at your Fontan case, and you're like, well, is there a small ASD? I can't see it. I can see why people would say it's not reliable. But I don't know. I mean, I don't know what your images look like, so I can't really say for sure, or what your protocols are.
I think our image quality would be okay. I think it's more just an overall comfort level with the idea that we can just, you know, toss out 2Ds and be happy with the 4D. Which yeah. I feel that way, but I kind of have grown up now with training with 40 flow, but some other people are less comfortable. So I think it's more of a transition type thing.
Yeah, no, I can see that. Sure. Definitely that can happen. You know, there's legacy knowledge, legacy experience, and you want to make a gentle transition there, especially if it's a little bit easier for new services, like where you're the only expert at the time, like I was at the time. Before there's a lot of other people involved, but if that being said, it's not like you can't make that transition too. One thing that makes the image quality better is being able to move the 40 flow sequence from the back to the front, because patients are more compliant early on. So my protocol, I can walk you through the complete protocol later, maybe after this case, to share with you what that looks like, because it sounds like that's important for you guys.
Albert, can I ask you a question?
Yeah.
You know, well, I just did, but a second question would be that I think that I'm one of those, I guess, probable relics that still does 2D PC in addition to the 40 flow. And I'm trying to wrap my head around the fact that I'm doing a short axis Fiesta stack, which is with, well, so let me start off by saying I do mostly, I'm working more with left-sided valve lesions than right-sided valve lesions. Mm-hmm. I've been taught to do the traditional methods of trying to, you know, backtrack and quantify, for example, mitral regurgitation. in the setting of AR, et cetera. So I've done a short axis Fiesta stack, which has all been breath held. And now I'm doing a free breathing assessment of left-sided lesions. I don't know if I can compare both of them. You know, I think I'm comparing apples and peaches here.
Yeah. So that is always a possibility for, I understand what you're saying. We did some experiments a number of years ago on the flow differences between an inspiratory breath hold and free breathing. And there can be, in some patients, a big discrepancy. And you'll see that especially in patients with Fontan circulation. You can expect to have a discrepancy if you do the difference between those two. I no longer have that problem because I do everything free breathing. The exception is the short axis stack, and occasionally, I would say 1 in 5, 1 in 10 times, you'll see a difference between stroke volumes that you get from 40 flow divided by heart rate. And LV and RV stroke volumes that you measure directly from SSFP breath health. So that can happen, but I mean the way to sort of mitigate these things is just more and more experience using it, and eventually you see that depending on your technique, you can really get that experience of whether or not that's still a problem. For us, it's not really an issue anymore. So I don't really think about it.
Albert, this is Lisa, if I may interject. Also, if we are trying to get the most physiologic measurements possible, our patients walk around free breathing. They don't walk around holding their breath. And then again, there's, the question of people who sit and walk vertically versus supine positioning in the scanner as well. But at least just deductively for me, free breathing numbers, I would hope, would be more representative of what the patient experiences just in daily life.
Yeah, I mean, so that is, I think that's correct. One thing to sort of remember and sort of summarize all these really important points is that in cardiac imaging, we observe a flow discrepancy and then try to rationalize and attribute something to that flow discrepancy. That's our sort of our natural process. This is sort of pre-40 flow. I had to do that a lot when I was a fellow. Like I would have 3 different measurements from 2D phase contrast and a different set of measurements from our SSFP data, and the measurements did not align, right? And I was like, this is insanity. Even the difference between 40 flow done, not 40 flow, 2D phase contrast planes done in slightly different locations. And you're left speculating at the reasons why none of the numbers match. And what I realized as I was working with 40 flow is that most of the physiologic reasons that we sort of attribute to things are actually not true. It's just the instruments are so bad. Like the background error in 2D phase contrast is so bad. And the SSFP measurements are so prone to measurement error that we've spent a lot of effort trying to rationalize why numbers don't match. And it's actually, most of them are not true. There's a glimmer of truth to a lot of it, but it's mostly that the instruments are bad. And 40 flow actually fixes that. Like I don't see those discrepancies like you do quite as often. I see it infrequently, and I can point out a couple cases where we have to sort of understand some of the technology. But for the most part, the numbers add up. At least in our hands, when we use this protocol, 350 for high velocity lesions and 150 for low velocity lesions, and 250 for in-betweens. So let me just walk you through Coarc a little bit, just to illustrate something slightly different, so that you're not left with only one example. And we can do this again. I mean, if this is helpful for you guys, I may make this a routine monthly meeting. I think maybe it's worthwhile because it actually helps me. It reminds me of where we've been and how far we've come by doing this, is because like all the questions you're asking are literally the same questions that everyone's asked when they first start. Like Lewis, who joined us, is one of our new faculty who was at Stanford as a fellow. Misha, Kate, Seth, they all now use 40Flow as part of our practice, but they had all the same questions that you guys have. But I keep forgetting because now they don't ask those questions as much anymore. But you guys are asking those, and they're the right questions to ask, but they're not really important as much anymore because once you're using it every day. So anyway, for a coarctation, let me just show you this. One of the challenges really, if you want to get a peak velocity, is that there's high velocity flow everywhere. You don't know where to measure with 2D based contrast, right? Like you can measure here, or you can measure here, or you can measure here, or you can measure there. There's a lot of places where you see flow acceleration on the SSFP, dephasing artifact, whatever. With 40Flow, obviously, you don't have to do that. You can just identify the location of the peak velocity by changing the color scale. If you have the bank to support it, then you can just make a cross section. I'll just show you what that looks like in this other plane. There is some aliasing, so you have to be aware. So in this case, it looks like there is aliasing, and I'll talk to you a little bit about what we do about that. But if there was not aliasing, I could just do a measurement like this, and it looks like I already have. At this location, I made a peak coarctation velocity measurement, and I got 3.2. But that actually is a pitfall because there is already aliasing right here. See, that's how aliasing manifests on the Arterys software. There's this weird little island, and high velocity in one direction next to high velocity in the other direction, and a sharp line in between. So this peak velocity of 3.2 and a gradient of 41 is actually not the peak velocity of the core. It's actually 3.5 or greater than 3.5, right? Because there's aliasing, and the bank is 350. So what I teach the other faculty and residents and fellows is that this is actually exactly why I choose 3.5, right? So what's the pressure across the pressure gradient across a lesion whose velocity is greater than 3.5? Well, by the modified Bernoulli equation, it's 4 times 3.5 times 3.5, right? Or 7 times 7, or 49. So why did I choose 49 or 3.5? Is that a severe lesion, for most cases, what most people conceptually understand, cardiologists, is one that exceeds 49, 50 millimeters of mercury, right? Once it's a severe lesion, there's almost no question you're going to do something about it, right? This is a coarctation that you're going to try to stent. Does it matter whether it's 57 or 63 or 49.5? Not really. For most people, this is a lesion that's going to get treated. So I choose a bank of 350 specifically for that reason, is when I see aliasing, then it's a severe lesion that will be intervened upon. Now, that may be different at a different institution. Some people may say, I actually do care about 5 millimeters of difference. Fine, but that's not our practice. So I've adjusted our expectations of our adult congenital cardiologists and other people that this is what we will provide. And it's a nice compromise, then I don't ever have to go to the scan. Hopefully that makes sense. Let me, feel free to ask another question while I load up another case here.
Albert, I think there was a question in the chat from Ryan, and I believe you addressed it right at the very beginning, but Ryan Avery is asking how long the 40Flow sequence takes, and I think you said 10 to 12 minutes, and then the type of coverage just being the three-dimensional volume that the techs set up without anyone having to go to the scanner themselves, any attending or resident or fellow. Yeah. So I wanted to address his question, and then I have sort of more technical questions, like in terms of the software itself, it runs via a web browser. I think you specified Google Chrome as preferred. Is that correct?
Yeah, so I think at this point, Arterys supports Google Chrome as the only browser. I don't know if there's some other initiatives to open up to Edge. I think we were discussing that a year or two ago, but I don't think that, Michelle, do you know if there's any other plans?
No, I think we've pushed that back in the backlog. Yeah.
Okay, so basically it's just Chrome now, and that, you know, for a number of years I did have to fight my hospital administration, not really the hospitals, mostly the radiology IT staff, to allow us to use Chrome. It was there, like, when I first got here, somebody took it off because they thought it was causing problems, but it wasn't, and then we managed to get it back on. Now, that being said, you can always use, and for us, sometimes it's easier to do this work at home. Our network bandwidth within the hospital sometimes has to be shared with a lot of other people, but I find even better performance at home or somewhere else. That's less of a controversial thing nowadays because a lot of people are working from home anyway because of COVID-19. But anyway, so.
Yeah, so that kind of leads into my other question, just in terms of rate of connectivity, rate of internet speed, and also does the computer you're using itself have to have any minimum processing capabilities that are sort of above just a standard, even a home PC or something like that?
No, in fact, it was in our very first demos a number of years ago. One of my co-founders got a couple of iPads and put them on people's backs at RSA. And those iPads, you can run the app through Safari, actually. So that's the other thing. Is on a Mac, you can run the Arterys software on Safari. So they implemented that. So those are the two browsers, I believe, Chrome and Safari. So you don't need special equipment, really. I mean, it's just any machine.
And then regarding the magnet itself, I noticed, at least in your immediate prior case you presented, it was obtained on a GE magnet. And my understanding is Arterys has a pretty strong relationship with GE. What about Philips or Siemens scanners? Is there any, like, are you vendor specific, or are you vendor universal, or
it's
somewhere in between?
pretty much vendor agnostic. I have seen a couple acquisitions on sort of research Philips sequences, as well as a whip from Siemens that look pretty good. Even better than the GE product sequence, I have to say. I do hope that GE makes some improvements because the other vendors are starting to catch up. Maybe exceed what the product, the GE sequence, currently does. So I would say that no, it's not specific to a particular vendor. In fact, one of the things that I want to encourage Arterys to do is to really get a champion site that is using Philips or is using a Siemens scanner, so that other people can learn from them on how to do it well. And you know, early on, this was thought of as a research thing, right? Not as a clinical thing. So the research guys have a very different focus for how they want to acquire 40-flow, and the Siemens whip was prospectively gated, so it was missing the first part of the cardiac cycle and the last part of the cardiac, either the first or the last part. So you didn't have a full cardiac cycle, and so you couldn't measure blood flow. And I thought that was really fascinating because what purpose do we have for phase contrast imaging if it's not to measure blood flow, right? But that was the way that the research sequence was built, because all they really cared about was the visualization of streamlines and stuff. They didn't actually measure the flow with it. So that's the reason why I really think that clinicians specifically, either radiologists or cardiologists, need to be the ones pushing the field, because if on the research guys have different emphasis, different priorities. They want to get more grant funding. We just want to take care of patients, and so we have different needs, and some of that is really simple, like just measuring the flow across the shunt, and it's not like rocket science or brain surgery. It's just something really quite simple. Let me walk you through our standard protocol, because that's come up several times now, and I think it's instructive to see how we're incorporating 40-flow into our practice. Like I said, when we first started, 40-flow was a sequence you added to the end after an MRA at the end of the a cardiac MRI, so like 2 hours into it, you're like trying to get the 40 flow running, and the patient wants a bail, and you're like, oh, hold on, it's just going to take 10 more minutes, and they're like squirming around, and you're trying to get something out of the 40 flow. So that's not the way we run 40 flow anymore. And often what happens now is after the 10-minute 40 flow and maybe a few more things, and the patient wants to bail, and I let them go. So it becomes a 20-minute MRI that you know, because the patients can't stay forever, they want to do a 20-minute MRI, fine. We do a 40 flow and a short axis maybe, and then they go, and that's the entire MRI. This is our standard protocol now for all congenital heart patients. And I also, like you, see only adults. Rarely do I see kids. I guess that's not an only, that vast majority of my patients are adults. A few kids, but not very many. Most of the kids are seen at our children's hospital. I'm trying to get them up and running with 40 flow as well. But the Arterys software has seen a lot of different iterations, and it's very fast nowadays. It's optimized for a combination of cloud compute, but also leveraging whatever local resources you have on your computer. So I start with a 3-pane scout, a quick SSFSE non-gated. This is just something you might use for body imaging. I may do an axial stack as well, but this is also not a gated sequence. So these are both in a breath hold. I try to minimize the number of breath holds that I do. Here's a vertical long axis prescribed off of one of these two, and you can see there's like a little hole in the heart here. This is actually a VSD, we'll see later. I think I read this case last week. You can see that all the cases are de-identified. This is a phonetic ID. So I can share with any other physician around the world. If you have an Arterys account, I can go up here and share my study. One of these, where is that study? Where's that button? Well, I used to have the button to share studies. Michelle, is it still up here somewhere?
So we've taken it out. I believe we can add it back in as a feature flag.
Okay.
I'm not looking to it.
Please do, because I use that. Yeah, I don't like it when features disappear on me. But anyway, so I'll use that, like share with colleagues in a different part of the world who might not have 40 flow and want to play with that case, or maybe collaborate. Like we wrote a paper with Erasmus and Jean-Francois Paul in Paris, and we shared cases and cross-read cases. So they shared with me and I shared with them, and then they did their measurements, I did my measurements, and it was like a multi-reader kind of a thing for ASDs a number of years ago we did. So that's a very easy way of collaborating across institutions if that's interesting to you. It handles T2. There's all this stuff for measuring T2, quick ROIs that you can place on the myocardium and plot the curves. Let's see if I could do this, wherever the curves are. Oh, there it is. So here's my 4-point T2, stuff like that if you want to measure the myocardial T2s. I just added the T2 map recently to our protocol. This is a new addition that I just do one slice. Here's just a quick scout for, so this is 1, 2, 3, 4, 5, 6, 7 breath holds. Then short axis perfusion. This is mostly for contrast timing. I think we do like 3 cuts, just a rest perfusion. And then I use this time, the delay time, once it hits the LV, to then prescribe a 3D cine, which is a cardiac gated MRA. This is the product G sequence, but I'm sure Philips and Siemens have something similar. Let me see if I can bring up so here's the cardiac gated. This is like a cardiac CT. So you could reformat it and I run this near isotropic, so I can, if needed, I can get function out of this, EF and whatever, or generate my 3-chamber, 4-chamber, or 2-chamber planes. This is sort of a solution to a problem where people thought 40 flow didn't have, wasn't, as pretty as their favorite conventional SSFP sequence. So if you wanted to bail after the 3D Cine and 40 flow, you can. So that's one reason I do this. But yeah, I mean, you can get short axis function, and there's a ventricular function in Arterys, and it's enabled to be able to get function out of 3D sequence. It's very helpful for things like small VSDs, or to look at coronaries, or look at PAPVR in an MRA. At some point, one day in the future, I may write a paper on this whole protocol. Anyway, so then I'll follow that up with an MRA. I don't know why this is showing up like this. Oh, here we go. Oh, nice. So yeah, there was a planning view that was thrown in there, but it's a pretty nicely full-featured viewer that Arterys has now, and you can do quickly 3D rendering off of any of these. So I'll follow the 3D Cine with a MRA. This is sort of a late phase MRA. So using the same contrast that was already given, just getting a second view, and then that's followed by 40 flow, which is here. I guess I ran it sagittal for coarctation in this case. So this is a more reduced field of view in this patient, dedicated to the aorta and coarctation instead of a full chest like I showed in the previous cases. And then I'll do my MDEs and short axis function and whatever afterwards. I don't know if we did short axis function on this one. I assume we did, but does that make sense for you guys? I have a couple different protocols I can share with you if it's relevant.
Yeah, that's really helpful for us. Thanks.
Yeah. Yeah, I mean, I don't know. What are your thoughts and impressions in the last 5 minutes here before we close?
This is Ibrahim. This has been really great. Gosh, there's a lot of questions I still have, but not enough for another hour. So I look forward to these. This has been helpful to start off for me.
Hey, Albert, it's Michelle. I think this was really good, and I think it will be helpful for a lot of users. Is maybe once a month or something. One thing that I get asked a lot from users is around like regurg jets and what you do, because I know you've shown me a couple of times. If you have a regurg jet that maybe you have to segment out by itself, maybe it's not being picked up in like your total flow or something. So maybe covering something like that. I know we're out of time for this call, but an idea for the next one maybe.
Yeah, I think that's a good idea. I mean, there's so many different uses of 40 flow and so many different clinical scenarios that we can maybe more systematically go through different topics. I mean, I can show you what I'm doing in this case in a patient with aortic insufficiency. It's very mild. I mean, visually, you can already see what let's see here. You can already see that this is not going to come out to very much flow. I can walk people through that process of how to analyze these cases. What's wrong button? Shift. Okay. So this is the AI, and the aortic insufficiency is half a liter a minute compared to an aortic output of like 4 liters a minute. So this is like very little. So anyway, yeah, I'm happy to go through that. I think it would be, over time, as there's more experience in the community, I would love to have other people present their cases as well, and get a feel for what's out there. There's a lot of tips and tricks for how to get the acquisitions to be better and higher quality, and I love to see the vendors catch up and produce better pulse sequences for us to use. So yeah, I mean, I'm happy to do more of these if that's helpful. Brad and Lisa, what do you guys think?
This is Lisa. I just wanted to say thanks to everyone for being here, and to Albert and everyone at Arterys and UCSD for putting this together, and also being open to my suggestion or request for something like this. I think this is really great. I'm really impressed with the sort of the smoothness and the quickness and responsiveness of the software, even in the midst of this Zoom conference. So that's been really nice to see. I'm sure I'll have more questions in the very near future after I allow my brain to rest for a few weeks here, starting July 1st too, after 10 years of GME almost. So, so yeah, I'd be excited to do this again. And also to see anyone's either interesting or exemplary or problematic 4D flow cases.
Yeah, I echo that. Thank you for putting it together, or organizing it, Lisa and Albert, for taking some time to really go through it. I do like the idea of doing this on a more regular basis because I think, you know, you're kind of one of the leading places here, I think, incorporating this clinically, but that's certainly always been my goal and my interest, and to kind of have a working group, a little bit of really clinicians. I know the researchers do a lot and have done a lot and have great organization around this, but I feel like the clinical side has maybe been not as organized from sort of a working group standpoint. So it'd be excellent to kind of learn more in this environment.